once again, this is the second chapter where we'll be learning about garbage collection. We're going to start by understanding the process that the garbage collector actually uses to determine which objects to collect. The mechanism is called mark and sweep. Next, we'll see that the garbage collection process needs to be efficient. This is to avoid big pauses in your applications while garbage collection takes place. And we'll understand how it achieves this by using something called generational garbage collections. Having this knowledge, we can revisit the idea of memory leaks that we learned about in the last chapter, and we'll see how to analyze what is in the heap to help us determine the likely source of the issue. We'll be creating a dump of the heap, a file which contains all the data currently in the heap, and then we'll use a tool to analyze this dump. And then finally, we'll mention the Perm Gen. You might have come across Perm Gen errors, which is a specific type of out-of-memory issue, and so we'll cover what these are also. But we'll start by finding out more about how the garbage collection process works. We think of garbage collection as removing from the heap those objects which are no longer reachable. While this is the end result, it's the purpose of garbage collection. Modern garbage collectors use a clever mechanism for achieving it. Rather than searching for all the objects to remove, instead the garbage collector looks for all the objects that need to be retained, and it rescues them. The general algorithm that garbage collectors use is called mark and sweep. It's a two-stage process. The first stage is the marking and the second stage is sweeping. In the marking stage, the program's execution is first paused. This is sometimes called a stop-the-world event. Marking cannot work properly if there are any threads still executing, so all the threads in the application are paused. The garbage collector then checks every single live reference. This is easy to do. It simply looks at every variable on the stack and follows its reference. The object that it finds at the end of the reference is marked as being alive, and it then follows any other references that that object has and marks those as being alive also. Once all the objects that are referenced are marked for keeping, a full scan of the heap takes place and the status of all the objects is checked. The memory occupied by those objects not marked or in use can then be freed up. And finally, the objects that are being kept are moved into a single contiguous block of memory. This stops the heap from becoming fragmented over time and makes it easier and quicker for the virtual machine to find memory to allocate to future objects. So it's interesting to note that the garbage collector doesn't really collect any garbage. It actually collects the objects which are not eligible for garbage collection. This means that the garbage collection process is faster the more garbage there is. If everything on the heap was garbage, well then the garbage collection process would be pretty instantaneous. So this is the basic process that modern garbage collectors follow, but it's not the full story. The problem with what we have just seen is that if there are lots of objects which are not garbage, then because garbage collection is a stop-the-world event, our application is paused while the garbage collection process runs, then the users of our application will probably notice that our application has frozen, perhaps for a few seconds at a time. This wouldn't be acceptable, so to avoid this, we have something called generational garbage collection. The starting point for understanding generational garbage collection is that most objects in Java live for a very short period of time. If an object survives one garbage collection, then it's more likely to live forever. We need to remember it's faster to collect when there's a lot of garbage, when there are few objects that are surviving. So generational garbage collection is a way of organizing the heap. The heap is divided into two sections. One is called the young generation and one is called the old generation. The young generation is typically smaller, but this can be tuned, which we'll see later on. New objects are created in the young generation space. The young generation will fill up quite quickly as it's small. When it's full, a garbage collection takes place, but only on the young generation. Because most objects don't survive for long, the young generation, which is full of new objects, is probably mostly garbage. So the process to garbage collect the young generation should be very quick. There are very few objects which need to be marked, and it's small anyway, so it should take fractions of a second. We'll not notice the application freezing while this takes place. All surviving objects are then copied to the old generation. The young generation is now empty, and any new objects can again get added to the young generation. The garbage collection of the young generation is known as a minor collection. Garbage collection will also run on the old generation, but only if it's needed, for example if it gets full. This is called a major collection. A major collection will be a lot slower as it's a much bigger block of memory to sweep, there'll be many objects still alive so the sweep will take longer, and the compacting process, the moving all the surviving objects into a contiguous part of the memory, will take some time also. So a major collection could take a few seconds rather than fractions of a second. We can view these generations using the Visual VM tool. So let's load that up now. I've got Eclipse running on my machine. It's not actually running an application right now, it's just the Eclipse IDE. In fact, I think it's still got open the project from the last chapter, it has, but we can connect to Eclipse and have a look at it there. So I'm going to open the Eclipse connection. And we'll start in the monitor and notice that Eclipse is well performing. It's using about 100 megabytes of memory on my machine. It's not growing or shrinking massively, so it doesn't look like there's a huge amount of garbage collection going on. But notice there's a Perform GC button here, which should force a garbage collection to happen. If I click on that, we'll see there we are. The amount of memory has decreased. A garbage collection did happen then. So that's showing us the amount of memory, it's showing us the heap in total, but let's see how to break that down into the generations. To do that, we need to install a plugin. So go to the Tools menu and click on Plugins, then go to the Available Plugins tab, and you want to select this one, Visual GC, Visual Garbage Collection. We'll click on Install at the bottom. That will take a moment to install. And click on Finish, and I think we need to close and reopen the connection to see the new tab which should appear here. So we'll click on Close and Open again. So we've now got another tab called Visual GC. Now this is split into two sections that are going to interest us. This area here represents the old generation, and this area here represents the young generation. We can see on the right that the old generation has allocated to it, in this example, 341 megabytes, and 84 megabytes are currently in use. Now the new generation is split into three sections called Eden, S0 and S1. It's slightly more complicated than the way I've just explained it. What actually happens is that when objects are created, they're created in this space called Eden. When Eden gets full, a garbage collection happens and the objects are moved into the survivor space, which for now just think of S0 as being the place where the objects that survive the garbage collection of Eden get moved to. The next time a garbage collection happens, when Eden gets full again, any objects that survive are added to the objects in S0, but just to make things quick, the whole thing gets moved into S1. So it's like the compacting process, the process that moves everything together, really just puts all the objects now into S1, S0 becomes empty, and the next time there's garbage collection, everything again gets cleared out of Eden and anything that survived gets swapped back from S1 to S0. And this explains why in the last chapter we ran out of memory without the line hitting the top, because some memory was reserved for S0 and S1, even though that area of memory was never actually used. Rather than the old generation being everything that survives one garbage collection, actually it's everything that survives, I think it's 8 garbage collections. So after an object has survived 8 versions of moving between S0 and S1, our 2 survivor spaces, then it gets moved into old. Now we can see as I've been talking that the size of the Eden space is growing very slowly. If I go into Eclipse and run my application, that should make Eclipse do some work. So I imagine we'll get some more data being used. So let's do that. We'll go into, I think it's Customer Harness, click on Run As and Java Application. I'm then just going to minimize Eclipse. Great, so we can now see that the Eden space has grown dramatically. We've got lots of objects in there. Because Eclipse is a well-performing application, there's nothing to worry about. Eden hasn't quite got full yet. And this section here that says GC time will tell us that, well, at least since we've been monitoring it, there's been no garbage collections needed. Just as I've said that, a garbage collection has happened. So we can see this little green bar here tells us a garbage collection happened. We can see Eden space got cleared out, and any of the surviving objects in the Eden space got moved into S1. I'm now going to stop and restart my application in Eclipse. Again, I'm just really trying to do something so that we create more objects and destroy them. So we'll click on stop here and run it again. And back into the profiler. So we should see the amount of Eden space grow as my application is running. Actually, it's not growing very much. I think what we'll do to try and force some more objects to be created and destroyed is do a clean in Eclipse. That will force everything to be recompiled. So we'll stop the application and we're going to click on Project and Clean. Just click on OK and again go back here. And well, we can see there was another garbage collection there. And in fact, our survivor space is emptied out. So everything we were using has been removed. It doesn't look like anything's been put into the old generation, but hopefully this screen is starting to make some sense. We can see when garbage collections happen. We can see our young generation and our old generation. Let's connect to the soft leaks application and see what happens with that one. So we'll start it running first of all in Eclipse again. And then in Visual VM, I'm going to close the Eclipse tab and we'll connect instead to Customer Harness. Go straight to Visual GC. Now this application, if you remember, is creating huge numbers of customers which immediately get destroyed. There'll be very little that's surviving. And I hope that this is what these graphs are showing us. We can see the Eden space is filling up very quickly. And in fact, it looks like there's almost continuous garbage collection happening on the Eden space, but there's very little going into S0 and S1. There's very little surviving each time there is a garbage collection. And anything that has survived 8 or more generations is being moved into the old generation, but we can see there's very little in there. So although there's an awful lot of garbage collections happening, actually there are very few objects surviving. The garbage collection is going to be very, very quick because it's almost all garbage. This will be an efficient application. I think it will be interesting to see what the heap looks like when we break it down into the old and young generations if our application is running in its broken mode where the objects aren't being cleared out of the collection. If you remember when we first started this application, the getNextCustomer method in the Customer Manager class was just doing customers.get. I'm going to remove the code we put in here and instead return customers.get 0. That was the broken code that we had when we first opened this application, and it meant that the size of the collection in this class just grew and grew and grew, and eventually our application ran out of memory. Let's run it in this delinquent state and see what the profiler shows us. So we'll go to Customer Harness again, run as. I'm just going to go in my run configuration and check that we have a limited size heap. Yes, we've still got the virtual machine argument that our maximum heap size is 20 megabytes. So we'll start that running and go into our visual profiler, and I'll need to close my existing connection to the harness and open a new one. So the first thing to notice, I think, is that the Total heap size we'd set as being 20 megabytes. We can see that 13.5 has been allocated to the old generation and the rest of it to the young generation. We've got 5.5 in the Eden space and 2 in each of these survivor spaces. Now, I think these graphs are very interesting. Firstly, the old generation is pretty much full. We can see, in fact, down here it is full. There's 13.5 meg allocated and 13.11 meg is actually being used right now. The Eden space is full and, well, really, I think it's given up. It can't move stuff into survivors. There's no point in doing so. In fact, there's more, I think, that would need to be retained from the Eden space than could go into the survivor spaces. So our application has pretty much crashed at this point. If I go into Eclipse, well, we'll see now that although it hasn't crashed, it still appears to be running. There are no objects being created. Our collection has reached its maximum possible size. We're not getting an error message like now. I think if we left this running forever, we'd eventually get an out-of-memory error. But this is a useful screen. It's telling us we can see straight away our old generation has filled up. We've clearly got a memory leak. There's clearly something wrong. Here's something for us to fix. When we have a problem like this, there is a further tool we can use to try and help us work out what's causing the memory leak. On the Monitor tab, there's a button here called Heap Dump, and that's going to save the entire heap as a file, and we can use another tool to open that file and investigate it. We'll have a look at that now. So let's click on Heap Dump, and we'll just give it a moment, and it tells us here where the file has been saved. So take a copy of whatever appears on your machine for the file location. So the tool that we're going to use to look at this heap dump file is called Memory Analyzer, or MAT, and it's written by eclipse.org. So you need to get it from the eclipse.org website. Go to the URL that you can see on screen here, eclipse.org/MAT. Don't click on this big orange download button up here. That will actually give you the page where you can download Eclipse. Instead, go to the link section and click on the download link here to download the MAT application. Now, there's a few different versions of MAT, so pick the version that's right for your machine. When you've downloaded it, you'll need to unpack it, and you'll see that depending on the version that you have, whether it's the Mac or Linux or Windows version, there'll be a file that you can run called Memory Analyzer. Because I'm on Windows, it's this one here. There'll be something very similar if you're on a Mac or a Linux machine. So we'll double click to run that file. Here's my Eclipse Memory Analyzer window that's now opened, and we can click on Close the Welcome window, File, and Open Heap Dump. And we'll paste in here the full location of the file that we copied from the Visual VM application. Click on Open. That'll take a minute or two to work through, and we just want to click on Finish with this first Leak Suspects report visible. Okay, now it does take a bit of time to work through the information here, and it's not always going to make sense without a bit of a thought. But what this is telling us right now is that of everything in our application, it does think there is a leak suspect. It's highlighted it as being one object that's taking up 14.2 megabytes of memory, with everything else taking less than 1 megabyte. And if we scroll down, we'll see that there is a thread which is keeping a local variable with a total size of 14.9 million bytes. That matches what we've just seen there. And it's telling us there's a stack trace of the thread. But if we click on this little details link, this is the bit that we might be able to use to understand what's going on. Now, this tree works a little bit upside down. So the object here, which is highlighted, contains the objects below it. So it's telling us that there's a thread object that's containing customer manager, that's containing array list, and it's the array list we can see that's using up 14.9 million bytes of memory. So it looks like our array list that is causing the problem. Now, of course, we know it's the array list that's the problem. We're going to see this tool in use at the end of the course in another worked example, so we'll get a bit more used to reading this tool. But I think that's helpful. We've got a full dump and we've been able to break it down and see that of all of that old generation, it's almost all consumed by this array list. So the array list is where the problem is. That will give us a clue as to what to fix in our application. I'd like to finish this chapter by returning to the statement I made earlier about the heap being divided into the young and old generations. There have been some changes to what I'm about to say in recent versions of Java, so I'm going to pretend for a moment that we're using Java 6 here, and then I'll explain what's changed in Java 7 and Java 8 shortly. So in the Java 6 world, then there is a further part of the heap called Perm Gen. This stands for the permanent generation. Objects which are in the Perm Gen will survive forever. The Perm Gen is never garbage collected. This means that if the PermGen runs out of space, then your application will crash. There are two types of object that go into PermGen. Internalized strings, we touched on these earlier in the course, that is strings which are placed into a pool for reuse, and every time we create a class, the metadata for that class is placed into PermGen. Now, I'm not going to go into any more detail about that last point. It's not the instance of the class. An object for that is created on the heap. But I want you to accept that for each class in our application, there is some memory needed to store information about the class, and that lives in the PermGen space. Now, you may have come across problems in the past where your application crashes with an error message saying that it's run out of PermGen space. This is an annoying error because when the PermGen runs out of space, it simply means that your application has too many classes or internalized strings. Unlike other out-of-memory errors, it's not caused by memory leaks or faults in your code. The only thing you can do to avoid a PermGen error is to increase the size of the allocated memory for PermGen within the heap. We'll see how to do that in the next chapter. It's worth noting that if you're running a server application, for example, if you're running a website using Tomcat, then each time you redeploy your application, if you make a small change to your code and you deploy that version to the server, even though many of the classes won't have changed, a new complete set of metadata for all your classes is created in the PermGen, and all the metadata relating to the previous deployment of your application is still in the PermGen but will never be referred to. Because there's no garbage collection on the PermGen, it will never get cleared out, and what this means is that if you redeploy onto a large server a number of times, eventually the PermGen will run out of space. For this reason, on a live server, you might want to consider stopping and restarting Tomcat or whatever your service application is each time you deploy a new version of the code to avoid the PermGen becoming full. So that was how the heap worked under Java 6 and earlier versions of Java. From Java 7, internalized strings are no longer stored in the PermGen. This change means that internalized strings are in the old part of the heap and can therefore be garbage collected. If your application uses lots of strings, then this won't be a contributing factor to PermGen crashes anymore. And from Java 8, well, in Java 8 they removed the PermGen altogether. Instead, they created something else called the metaspace, which is where the metadata for your classes are placed. The metaspace is a separate area of memory, and it's not part of the heap. Instead, it's allocated out of your computer's native memory, so the maximum available space for the metaspace is the total available system memory for your computer. Now, there is an option to cap the maximum size for the metaspace. If you don't do that, then the virtual machine will just grow the metaspace as it needs to. But a useful feature of the metaspace is that when classes are no longer creatable, the metadata related to those classes is then removed. So this means that if you're running Tomcat, for example, under Java 8, then every time you redeploy, all the old class metadata in the metaspace will get removed and the metaspace won't grow and grow each time you redeploy. So at the time of this recording, we think that this will remove the old PermGen style problems on a server. Although on a live server running Java 8, you might want to keep an eye on how much memory your app is using over time. Whilst it should be okay, because Java 8 is not yet widely used on production servers, there could be some unidentified issues that haven't yet been widely reported. So that covers garbage collection. We now know quite a lot about how garbage collection works, and we've seen that it's a very efficient process. The mark and sweep approach means that rather than destroying objects, the garbage collector actually retains those objects marked as still in use. So the more garbage there is, the quicker the garbage collection process will be. And because it operates using generations of objects, that is, new objects are created in the young generation space, and if they survive garbage collections, then they're moved into survivor space and then the old generation, so the many objects that have a very short lifetime should be garbage collected quickly, and the virtual machine doesn't need to check objects that have survived for a number of generations unless it really needs the space. We saw how to make a heap dump, a file containing whatever is in the heap at a particular moment, and then how to analyse that file using the memory analysis tool. And we saw that this gives us a clue as to where to look in our application for potential memory leaks. We'll be doing some further work with this tool in a later chapter. And finally, we talked about the PermGen and the metaspace, and hopefully we now understand what PermGen errors are. In the next chapter, we'll be looking at options to tune the virtual machine, and one of these options will be to alter the size of the PermGen space. So I'll see you in the next chapter.